Hello. I can't hear you guys.
Sorry, just give me a second. No. Hang on. Yes.
Yeah. Am I audible?
We cannot hear you. But perhaps they're still setting up
Okay.
in the background. Give us a second. Perhaps you can already share your slides.
Are my slides up?
Yes, we see them now in full screen. We will need a second. Can you say something?
How about now?
Now we hear you.
Okay.
Okay, the floor is yours.
Hi, good afternoon, everyone. I'm I'm Marvin, and today I'll be sharing a book, Topogos Political. First, I would like to thank my collaborators from Triple IT Hyderabad and DeepMind India Lab. So, a quick TLDR on what our work is about. Uh, we we aim to do controversy detection, and the way in which we define controversies, at least quantitatively, is something that I'll cover later. But qualitatively, what we want to find out are discussions that have equal opposing and supporting views, and this is the definition of controversy that we'll stick with for this work. The thing about controversy detection is that it is bounded culturally, contextually, and temporally. Something that's controversial in one group of people might not be controversial in another group. And it could also depend a lot on the current situations going on. And it can also depend on previous discussions. So, controversy is an umbrella term, but to do something meaningful, you'll have to ground it in all these three aspects. So this is why we scope our work to performing controversy detection, specifically on Reddit in the context of Indian politics. So all the data that you'll see that we perform our experiments on are from Reddit and are from Indian subreddits around the election time. So this was one of our major goals for the project. We wanted to just do a quick study on how is the discourse around the time of elections in India, especially in Reddit, because Reddit is not was not a popular platform in India back then during the last elections or so, and it's gaining popularity recently. So we wanted to see how much how has the discourse evolved on Reddit in the Indian context. And what we do unique is we use topological data analysis, particularly persistent homology, And we curate features from this to help do better controversy detection. And the next natural question is, why would we want something like that? Why can't we stick with the traditional features that are used already? So this is what we hypothesize. We hypothesize that the final structures or patterns that you see in the post interactions are not representative enough, especially when you don't have when there's a lot of class imbalance and you don't really have a lot of good rich samples for controversy when compared to non-controversial posts. And it follows that we also hypothesize that the evolution of a post interactions over time conveys much more rich information than the final evolved state alone. So this is our entire goal on why we want to use topological data analysis. And the third thing that we also explore is identify the pitfall of artificially balancing the data. So what we observed is a lot of fields in this work go out of their way and collect a real world data set, but rather when evaluating their work, they try to artificially balance it either by undersampling the non-controversial class or by oversampling the controversial class. And we observe that this behavior misguides the numbers that we end up seeing. So in our work, we also try to ground it in a way that it mimics the real world statistics, where there is like a lot more non-controversial posts than controversial posts, and you want to perform reliable, robust detection in this setting. And as a bonus, we also do introduce something called the imbalance impact score, which is just a quick measure, which is just a naive way to measure how much of a performance difference there is between the balance setting and the imbalance setting. So we take the same data set, same method, we evaluate it in the balance setting where the data set is artificially balanced, and then we also balance it in the evaluate it in the imbalance setting where the actual statistics of the data set are preserved. And this difference, we use it to calculate the imbalance impact score. And higher the score is, the more robust your method is to handling data with real world statistics where there's a lot of imbalance. So now I'll just go into detail of each one of these parts. Starting with the data set, like I had mentioned, we curate our data from popular Indian subreddits that usually engage in political discussions. Of course, this is like a very loose way of defining political discussions because there could be much more going on in these subreddits than just political discussions. But so what we rather end up doing is we initially collect a seed set of keywords and we try to see if the post has at least X number of these keywords before calling it a political post, even if it's from a political subreddit. And we also do other kinds of pre-processing to remove to remove low quality posts. That is something, for example, that we do, which was the harshest filter, was disregard all the posts with less than 5 comments, because we believe that posts do not gain enough attention or uh, not of high quality for the setting that we want to study. So these are the subreddits that we look at. We look at 7 subreddits, and in total, we collect around 20,000 posts. And this, for reference, is larger than the existing data sets in this domain. So, another contribution of our work is presenting a new data set which is large enough to conduct SOTA research on. And if you look at the number of controversial and non-controversial across datasets, the average, it averages around 10% being controversial, 80% being non-controversial. And the way in which we define controversial and non-controversial is something that I'll cover later on. So for now, just assume that we have a method to find out how they're a ground truth method to find out how they're controversial and non-controversial. And the neat part is with the 20,000 posts, we also get around 1 million comments associated with each of these posts. So this is quite rich data. So what ends up happening is this 20,000 that you see here is after these filterings that I have mentioned, after the keyword filtering and the comment filtering. But our initial data set had around 60,000 posts, and here are some of the data set statistics. Each post on median on average has around 20 comments, which we believe is a very good number to study the temporal evolution of. And this is how we label a post to be controversial or non-controversial, the ground truth label before our method is even applied. So we need a way to evaluate our method. For that, we need ground truth data. So this is how we do it. So we label data using Reddit's own filtering algorithm. Reddit has its own way of defining a hot post, a top post, and so on. So we leverage that to find the controversial posts. So the way in which we collected this data was through a Reddit API, which also gives you multitude of other options to look at. And so a metric that we went by is something called the upvote ratio. This is basically, so if you're unfamiliar with Reddit, an upvote is when a user likes your post, a downvote is when a user dislikes your post, and what is finally displayed to the user is displayed to any other user who's viewing the post is the number of likes, number of upvotes minus the number of dislikes, the number of downvotes. So the final number that you see uh, in a post is the subtraction of these two. But what we also rather get from the API is something called the upvote ratio, which is the number of upvotes by divided by the total number of votes in the post. So we have previous research to support us on why this is a good metric to establish ground truth, controversial and non-controversial posts, because intuitively you can think of a ideal controversial post having upvote ratio of 0.5, which means equal number of people liked it as the number of people who disliked it. So there is like a mixed opinion about it, and that exactly fits our definition of what a controversial post is. So for defining the ground truth controversial post, we use the upvote ratios. And what we rather do is like we take this upvote ratio spectrum and we define ranges which belong to the controversial region and ranges which belong to the non-controversial region. So the figure that you see on the left is a toy experiment that we conducted that's not on the real data. So we did a small qualitative experiment on a representative subsample of the data where we manually looked at the data to find out good thresholds for the controversial posts. And this is what we ended up with. Anything between 0.3 and 0.7 is considered to be controversial. And if you remember my intuition from before, having a upward ratio of 0.5 exactly corresponds to having equal number of likes and dislikes. So anything between so we give it a bit of a leeway, and anything between 0.3 and 0.7 is considered to be controversial. And anything above 0.8 is considered to be non-controversial because popular posts are often non-controversial and popular posts have high upward ratio. And we ignore anything between 0.7 and 0.8 because that's a gray region, and it's when we qualitatively looked at the data, it's often 50-50. It could be controversial or it could be non-controversial, and we didn't have a reliable way to separate them, so we just ignored that chunk. We also ignore the chunk below 0.3 because these, again, qualitatively looking at it, were very low quality posts. That is, most of them were advertisements, spam, stuff like that, even if they have the political keywords that we were filtering with. So yeah, the final way in which we define controversial posts, ground truth controversial posts, is that we look at this very specific value returned by the API. And if it's between a certain range, it's considered to be controversial. If it's with another between another range, it's considered to be non-controversial. And the stuff that you see on the right is from the actual data set. Again, the stuff that you see on the left was just a preliminary experiment that we conducted, like a qualitative toy example experiment. And the one that you see on the right is the actual data set statistics. Yeah, now moving on to the core meat of our paper. So what we explore is twofold. One, we look at the features that were used in the previous works and we evaluate how good the features are. And we also add a new feature, which is which is inspired by the topological data analysis domain, which is persistent homology. And we see how well this newly introduced feature fares with the already existing features. So we have textual features and graph-based features, and persistent homology would be addition to the graph-based features. So once these features are established, we also pass these features to the popularly used models in this domain. So we chose this subset because they were the most used in prior literature. So we have three GNN-based methods. We have 4 traditional ML-based methods and 2 baselines, which are much more complicated than uh, all of these methods. And first, I'll focus on the features that we build. Next, I'll go on to the details of the models that we evaluate with. So starting with the textual features, so when you have a post, you obviously have textual information associated with it. And the first feature, F0, that we build is a vector containing information about the post metadata, such as the number of upvotes, the number of downvotes, the number of comments, the in degree, the average in degree and out degree of notes in this post, and so on. We have this entire list in our paper. It's a vector of size around 10, I believe. So this would be the first feature that we construct. Uh, I'll skip F1 because that comes under graph, so I'll directly go to F2. The third feature that we construct is something super simple, rather naive, is the post comment embedding. So what we do is we just take the post, append all the uh, uh, so we take the post, just the post alone, the stuff that you see on the right, the topmost post, and we embed it using sentence word, and we get a dense embedding, which we use as a feature vector. That is F2. And F3 is common content embeddings, which is we append the post along with the rest of the comments, the comment text in the entire post tree, and then we embed this whole entire paragraph. And that would be F3. We again embed it using sentence word. So these are the textual features that we use. Next, moving on to the graph features that we use. So first I need to clarify the graph that we construct, because this is not exactly the graph that one might think. So it is not a so the graph that we construct is rather a user-user interaction graph, where each node is not a comment, but rather a user. And an edge exists between a user, a directed edge exists between a user. If a user A has replied to a comment made by user B. It could be any comment within the post. And yeah, that's how an edge is defined. So actually something that we also tried out was construct this graph on two levels. One is the local post level, where we do where we construct this graph locally. That is, an edge exists between two users only if they have interacted within the scope of this post. What we also do is something called the global level interaction, where an edge exists between two users if they have interacted in any of the posts in our data set. But finally, the stuff that you see on the paper is the is the global interaction graph. And with this established, with what the graph is, with what the graph is being constructed with and how it's constructed, we now have something to look at, some kind of graph to look at, and something that is also super important to notice. All these edges are temporal. That is, we have a timestamp on when this edge was created. So this is not important for static graph features, but they become important for persistent homology, which I'll cover later. So that's something that I missed to mention. So the feature F1 that we construct are graph motifs. These are quite simple. These are static graph features where we look at the final post structure. That is after the final timestamp, and we count the number of occurrences of each of these predefined motifs. So basically what you would end up having is a 13 size vector, and each element would be count of the number of occurrences of this particular motif. And if you look at the example that you see on the top right, the corresponding one is displayed below it. So the orange highlighted motif corresponds to motif 11 that you see on the left, and the blue highlighted one corresponds to motif 12. So this is what we end up doing. So we have this vector of 13 dimensions, which conveys structural information about the graph. Finally, this is the feature that we add, F4, persistent homology. So if you're not familiar with topological data analysis, basically persistent homology is a method to quantitatively describe births and deaths of features. Births and deaths are official terms, by the way. Births and deaths of features, graphical features in topological data. It is general enough to be used for other kind of stuff as well, like point clouds, but we rather adapt it for graphs here. And I'll go on to more detail on what this persistent homology is. So I won't go into the math. The math is pretty neat. So basically, a quick intuition is that what you end up doing is, instead of looking at the final structure, you go from timestamp 0 to timestamp t, and then you look at the features that are born using during certain timestamps, and when they die during certain timestamps. Something that could be super trivial is you keep adding an edge in a circle, and then this new loop is born at timestamp t, and this loop is dead when there's another edge connecting between the circle, within the circle. So, or rather, two loops would be born. One loop, the entire big loop would die, and when you connect it within the circle, that big loop will die, and two smaller loops will be born. So the basic intuition of persistent homology is to capture such topological features. And in our context, what we want is to capture the evolving nature of discussions in the user-user interaction graph. So this is basically our hypothesis or our intuition. So repeated back and forth exchanges amongst small group of users can form loops in this interaction graph, like you see. 12 and 11 are small loops where users talk amongst themselves. This could mean various things like these users are constantly engaging in a heated discussion or intense disagreements, or it could also be positive, but we do some qualitative analysis and we find out that this is usually corresponding to disagreements, and that we believe is a useful feature that we want to leverage in our pipeline. And this is a quick GIF on how persistent homology works. Basically, the birth and the death stuff that I talked about. I won't go into many more details here because I believe it requires a lot of context. But what we rather end up getting after applying persistent homology is something that you see on the right. You actually get a graph, and that's all you get out of it. You actually literally get a graph. And the way in which we use it as features is something called a persistent image. I think this got popularized back in 2017 or something, where we try to um, literally embed this graph that you see on the right as an image. But we rather do it slightly intelligently, where we diffuse Gaussian noise from each of the final points that you have. So you rather not only have points, but rather a gradient over it. So what you rather end up getting is an image that describes the temporal evolution of a network, and we vectorize this image. So, and that would go as our feature F4. I think we have some math on how we did it in the appendix. Cool. So just summarizing why persistent homology, it in other domains, it has been shown that it can efficiently model temporal evolution of anything. We just adapted it to our problem statement. We effectively model the temporal evolution of discussions by analyzing the topological features across multiple time scales. And we wanted to see how the conversations develop over time. And we wanted a neat vector representation, which basically condenses as much information as possible about the entire evolution of discussion. And persistent homology has neat corollary features also. Uh, it has been shown that they are robust to noise. Noise here would correspond to having faulty timestamps or something. And there are some results that show that it is quite robust to it. And the main selling point is that it has been shown to be very good at capturing multi-scale interactions. Um, in other domains, multi-scale in this case would be like between groups, between smaller groups, between larger groups across time scales. So finally, concluding the persistent homology stuff, what we have as an input is a graph where we have timestamps for each of the edges, and what we have is an output. The out Have as an output is a vector, just a dense vector that we have. But if you backtrace it, that vector corresponds to a persistent image, and that persistent image is created using persistent homology or using filtration. Yeah, more details in our paper. And these are all the features that we have. We have F0 to F4, 5 features that I just described. And now we'll move on to the models that we test across. So our intuition is to basically take all these features and test combinations of all these features across all these models and see if persistent homology actually adds any value. So now I'll just quickly go over the models that we test. We use traditional ML models that were used in, like, I would say, the oldest part of this literature. AdaBoost, something that's very robust, random forest, MLP, and something else that we wanted to try that others didn't was modeling this as an anomaly detection problem, because there is like a huge disparity between the controversial setting and the non-controversial setting. If you remember the data set statistics, it's around 12.9%. On controversial posts are only around 12% in the entire data set. So we tried modeling it as a controversial anomaly detection problem. And we tried two methods actually, only one of it made it into the paper. We used Gaussian mixture models, GMMs, to model the distribution and model the distribution of non-controversial posts. and classify anything out of distribution as controversial. But we empirically found that autoencoders can do the very same stuff, but more effectively. So what we rather do with autoencoders is that we train an autoencoder to mimic the distribution of non-controversial posts. And when we try to do a forward pass on an we basically calculate the autoencoder loss on for a new incoming post. And if the reconstruction loss is high, it means that it has not seen this sample to be in its training distribution, which would mean that it is a non-controversial, it's a controversial post. That is, it is not from the distribution of non-controversial posts. So that is why we have an autoencoder here. And for the graph models, we just use popular GNNs that were used in the literature. We use a simple GCN, we use a GAT, and we use GraphSage. So the graph that we run it on is the post graph here, not the user interaction graph. The post graphs are the one. So there are two graphs that we tried it on with. One graph is the post graph where the nodes are posts, and another graph is the user interaction graph that I mentioned before. Again, what made it into the paper was just a user interaction graph with node embeddings initialized. So the node embedding here would be the textual embedding of all the users' posts. Yeah, that is how the graph is constructed. And finally, we also tested across two baselines. Unfortunately, there aren't any reliable good baselines after these two. One is from NACL 19, another one's from ACL 20. So we use these two baselines. One is TPC GCN, which first identifies topics, creates meta nodes for topics, and then reconstructs the graph with these meta nodes to ease the information flow between posts from the same topic. And another baseline was proposed in the paper is called Something's Brewing, that was more analytical than this. So as I'm running out of time, I'll quickly cover the experimental and evaluation settings that we have. So we have three training settings. So the first one, the capital A, is we balance the data set by random unsampling of the non-controversial posts. B is we balance the data set, but we upsample by random oversampling of the controversial. So we do a midway basically. So we do some oversampling, some undersampling for them to meet in the middle. And C is training with the original class distribution. So we have these three different training settings. And for testing, we again have two settings. We test on a balanced data set, and we also test it on an unbalanced data set, that is small a and small c. So we have 3 × 2, 6 settings in total for each method to test it on. This is not very important. In the interest of time, I'll quickly gloss over it. We also introduced something called the imbalance impact score. More details in the paper, maybe I can also take it in the questions, but basically it measures the performance drop when going from a balanced setting to an imbalanced setting, but it also accounts for performing well in both. So if your I score is high, that means you not only perform well in each of these settings, but you also do not lose a lot of information, a lot of drop in performance by going from one setting to the other setting. So quickly going over the results. So these, we obviously tried all kinds of feature combinations. We have like what, 4C1 plus 4C2 plus 4C3 plus 4C4. As we have 4 features, 5 features, we ignore F1. I'll also cover on why that's the case. Yeah, we only in the paper, only some combinations made it out to the paper because the others weren't good enough or didn't convey enough information. So the takeaway from here is that for all the models that you see, you only see AdaBoost, MLP, and Random Forest here. I'll show the other ones there. So the takeaway here is that when you add F4, the very last column, you see the the F1 score of the controversial class being the highest. And you also see the I value being the highest, which means that when you add F4, the topological features that we proposed, you not only perform the best amongst on detecting controversial data, but you also rather ensure that when you go from from a balance setting, artificially balanced setting to an actual imbalance setting, you do not lose much of a performance. So that is why we construct this I metric to basically put two of these objectives together into one. So in almost all the columns, basically what you need to look for is the bold value here. Almost all the in all of the settings, you see the bold value being when F4 is added across different training paradigms as well. So our model, the feature that we propose is pretty robust to data imbalance while also being rich enough to increase the performance. And this is the result for autoencoder. And as always, when you add F4, the value becomes the best. And this is for GCNs, the GNNs, GAT, GraphSage, and GCN. Again, you see the value being the best, except for this specific case, it being best for the base model plus when you add the topological features to it. And yeah, basically the bolded values still show that it adds a lot of value even in the case of GNNs. And that is the same with baselines as well. Unfortunately, we cannot add our features directly into TPC GCN. So what we rather show is when we use SV here is something brewing's method. When we add, fortunately, we can plug in our feature into their pipeline, and we see that when we do that, we again get the best performance out of all. Once again, just a quick reminder of what you need to take away. The takeaway here is that when the I value is high, it means that you not only are the best at detecting controversial class, but also you're good at ensuring you're robust to data imbalance. Quick conclusion, we introduce a new data set. Reddit Indian politics, we have it public. You can download it and use it if you want. We also see that class imbalance of controversial data causes a huge drop in performance in the existing SOTA models. Addition of persistent homology features improves the robustness of controversial post detection. Robustness here would mean robustness to the data imbalance. And we also validated our hypothesis that the evolution of a post conveys much more useful information than just the final state. And this is our archive link. And thank you. I'm open to questions now.
Thank you. Questions? Don't be shy. Perhaps I can ask one.
Yeah.
Um,
Sure.
so at the end, you were very fast when you were explaining the imbalancing score. Can you expand a bit more on that?
Okay, cool. So like I mentioned, the imbalance score has two objectives. One is to ensure that the performance on detecting the class imbalance, the controversial post is good. And that is what can you see my cursor by chance? Yeah,
Yes.
you
Yes.
can. Yeah, so the first term that I'm circling over basically awards if your basically SC that you see here is a measure of how good the controversy detection is, which is like the F1 score of the controversial class. So the first term basically multiplies these two, which means it awards if you have a high score in both of these settings. If you remember, setting A is when you test it on a balanced data set. Setting C is when you test it on the original class distribution with imbalanced data. So by multiplying these two, we are basically forcing it to award if both of these values are high. And the second term that you see here is it penalizes if there's a huge difference between these two settings. So we have this multi-objective thing that we go on. gone about. So it's as simple as that. We wanted two objectives to fit in one objective function. We just multiplied these two functions. Yeah, if that makes sense.
Yes, thank you. I don't see other questions.
Okay.
Thank you. Thank you very much.
Thank you. Yeah, the archive link is here. Thank you.
Okay. The next presentation is by Yasin. Yasin, can you hear us? I will promote you to panelist. And
Hello.
hi.
Hello. Is the sound fine? Can you hear me?
Yes, we can hear you.
Okay.
I know it's very early in France, and
Yeah.
I heard you had a really long night.
Yeah, actually very long
But
night.
yeah,
I
now
was afraid
the
to miss
floor is
the...
yours. You can share a
Okay,
screen.
thank you. So let me show you my screen. Yeah, okay. Yeah, so I have to quit. I have to give permission to the Zoom meeting to access my screen. So I'll be quitting and rejoining.
Okay. What should I do?
Remove him from
He's not here at all.
He left Zoom now.
Yes, he left.
Okay.
And
Yeah, he's back. Yeah.
okay. I will promote him.
Yeah, now we can promote him.
Hello, so I'm back.
Hi, yes. Can you hear
Yeah,
us?
yeah, I can hear you guys. I should have no problems now.
Yes, welcome back.
Thank you. Okay, so can you see my screen?
Yes, we can see you can. Yeah.
Okay. So hello everyone. I'm sorry for the brief delay. And I'd like first to thank you for attending this presentation. My name is Yasin Tarai, and I will be presenting our work on emotion-driven fake news detection, where we propose a new approach called intermediate layer emotional representations, or in short, EILER. So unfortunately, my co-authors, who also happen to be my thesis supervisors, and I were not able to attend in person. So this presentation will be virtual. And here is the outline of the talk. I'll first introduce the motivation behind using emotions for fake news detection, then show some emotional analysis on a benchmark dataset. And finally, I will try to present our method and some experimental results. So fake news often spreads, not just because of false information, but also because it can trigger or steer strong emotional reactions. However, most of the existing methods tend to overlook emotional signals or how reliable and nuanced they really are. So this motivated us to propose our own method to capture emotional signals, which is EILER, or the intermediate layer emotional representations. And we believe that our method actually improves fake news detection by combining publisher emotions and social emotions, which is not new. But what we are doing different is that we're doing this at a deeper representation level. So we will start first by talking about emotions and reactions to fake news on the relations between all of those. And emotions can be powerful markers of fake news. Previous works like emo ratio, EmoCAD, and dual emotion features leverage emotions for fake news detection. And while fake news often triggers stronger reactions, such as joy, anger, and surprise, it can also it can also tend to generate more neutral approaches or neutral reactions, which is sometimes confusing for us. So we wanted to come up with some kind of reliable feature that would enable us to detect fake news on the long term, because as we know, topics do change, truths do change over time, and the context also do change. So for example, what is true today might not be true tomorrow, and we believe that emotional reactions stay with us and could be a reliable feature for the long-term fake news detection, as we just mentioned. So we will start our analysis, or we start to establish a basis for fake news detection using emotions, using the fake-edit dataset, which is a dataset that is from Reddit, and it contains over 1 million samples and their associated comments. And while the dataset offers multiple levels of granularity of labels, we only use the binary classification setup in this study. So we only use labels fake or not fake. And this is not relevant to our study, but if you want to use the corpus, it is also multimodal, so you can use pictures, videos alongside the different news articles and content that is available. So here is an example of what we can find in the fake-edit dataset. This is this is supposed to be a humorous fake news post about Mark Zuckerberg that says, Mark Zuckerberg announces all of Facebook's future decisions will be made by the Cube of Justice. And we can see that even satirical fake news such as this one can stir up strong emotional reactions, as we can see, for example, in the in the third comment, all hail the Cube of Justice, which contains all hail, which is a very strong emotional reaction in wording. And also, for example, the last comment that is glorious. So this is the kind of data that we'll be working with for our initial emotional analysis. And here we'll be comparing the distributions of reactions in the comments between real news, legitimate news, and fake news. So on the left, we have a histogram of emotions expressed in reaction to legitimate news, and on the right, we have a histogram of emotions expressed in reaction to fake news. And while we can see that there is some similarities, for example, a predominance of anger and joy in both of them, we can also notice that there is some kind of difference in the proportions of those. So we might want to ask ourselves, are these distributions statistically different or not? Are they just the same? And the question is answered very fast as we formally test the difference between the two distributions using a chi-square test, and we get a very small p-value, which invalidates the null hypothesis. And another question asks itself, but it's only out of curiosity, and it is what emotions specifically do make the difference. And in order to choose, or in order to tell what emotions do make the difference, we have to put ourselves in the context of what we call the Parrot emotion framework. So most of you must be, I think, are somewhat knowledgeable about the Ekman framework of emotions. So this is almost the same, to the exception of one emotion, which is love. And we can see that, for example, in the Parrot framework of emotions, there are six emotions, the 6 basic emotions, which are joy, anger, fear, sadness, surprise, and love. And by repeating the chi-square test, for each of those emotions, we notice that there are 3 strong emotions that do stand out, which are joy, anger, and surprise. And this aligns with observations in the literature about emotional reactions to misinformation. Okay, so here we are done with the initial analysis of emotional reactions to fake news. And we've established that there might be some relevance to using emotional reaction to detect fake news. So given these findings, we attempted to detect fake news purely based on emotional signals. And in order to do that, we created simple vectorial representations using the emotion distributions from comments. And this approach represents each news post by its aggregated emotional profile. So we get very simple vectors for each post based on the emotion distribution on the comments in reaction to that post. And we obtain an emotional distribution for the whole corpus, or the subset of the corpus that we're using for the study. And we'll use this distribution in order to train or fit simple classifiers to get a feel of what the results could be using only emotions for fake news detection, and we get the following results. So we have here 4 basic models, 2 logistic regressions. The first one using the 6 emotions, the second one using only the top 3 emotions. We also train a boosted tree and a deep classifier, which is basically the best performing MLP we found. And why we noticed that there is some improvement between the logistic regression of 6 emotions and the logistic regression of 3 emotions. The results are kind of weak, and it leaves us a bit skeptical about whether relying solely on surface level emotions is really the right choice. Sorry. So this had led us to try and come up with a better approach in order to capture emotions, because there seems to be relevance, but we couldn't capture it using only very simple emotional signals. So we want to capture deeper and more abstract emotional features of fake news detection, which has led us to introduce EILER, since we believe that important emotional cues get lost during the emotional labeling process. So between the text and the output of either manual annotators or even machine learning models such as BERT classifiers. And in order to get a better feel of this, we decided just to add an intermediate layer to our classifier of size D, a size that we can choose manually and through many experimentations. For our case, we choose a size of 64 in our paper, if you read it, and I invite you to read it. And the goal is to preserve some richer emotional information and a more abstract one also, because since we're talking about emotions are also considered an abstract concept. So it goes without saying that maybe we should try to give a more abstract representation to a more abstract concept. And our hypothesis is that emotional labels are simplified interpretations. And inside the network, much richer emotional representations are formed, or we think that much richer emotional representations must be formed. And so we aim to capture these internal patterns by extracting the intermediate layer output that we just added. And then we move on to building either using this intermediate layer emotional representations. So for each news article and its associated comment, we extract the Euler representation. We aggregate comment representations using max pooling, and then we try to aggregate the comments representation with the piece of content representation. And here in our case, we use the concatenation as a tool for aggregation through experimentation. So here, for example, we have a table that justifies the concatenation in the step 6. As we can see, the concatenation gives us the best results, and we compared pooling techniques such as min pooling, max pooling. We also use the difference, and we can already see a jump in performance because we went from F1 scores of around 50 to 60 to F1 scores of 86 and precisions of around 80. So we think that using this method or this representation method, we already get much better results, and we can see the relevance of using only emotional signals in fake news detection. Okay, so now we've established that emotional representations might work for fake news detection, and we have to compare it first to other emotional representations, because we mentioned that work has already been done. So we will compare it with the state-of-the-art emotional representations, specifically in the context of fake news detection. And we find 3 main approaches, which are emo ratio, which determines the emotional tone by calculating the ratio between negative and positive emotional words in the content of news articles. Emocred, which uses emotional lexicons and text intensity features based on the frequency of lexicon terms occurrences. And dual emotion features, which is the most recent one and the most complex one, which exploits both author's emotions and social emotion, just like our method do. And it consists of 3 components: publisher emotion, social emotion, and the emotion gap. And while each of those methods actually captures the emotional signals differently, they all rely on the outer final interpretation of the emotions, while our method taps into internal emotional abstractions, which is the main difference. So we're using internal features that we think are richer than whatever they are trying to do, because they do construct their features based on already annotated words or a piece of text or content. And since we'll be evaluating against different methods, we'll also be evaluating on the corpuses that they have published the paper in. So we'll be using the Rumor Eval 2019, which was introduced at the SemEval 2019, which is a task in ACL. And the dataset contains over 400 news articles and around 8,000 associated comments collected from Twitter. It goes without saying that this was in English. And we also use the Weibo 20 corpus, which includes